For millennia, people have wondered about the origin of the universe. Armed with modern science, we are closer to understanding the greatest cosmic mystery: what caused the Big Bang? Our universe began 13.8 billion years ago. But what prompted this cosmic birth? What came before? In this documentary, we explore the founding theories and compelling evidence as we search for answers to the most fundamental question: what caused the Big Bang? The Big Bang theory is the most common scientific explanation for the origin of the universe. This suggests that the universe began in a very hot and dense state, about 13.8 billion years ago. At that moment, all matter, energy, and space began to dissolve. This expansion continues today and is supported by several lines of evidence, including the observed changes in distant galaxies. In the first moments after the Big Bang, the universe was a chaotic environment of high temperature and density, where particles such as protons, neutrons, and electrons formed. As the universe expanded and cooled over time, these particles began to combine to form simple nuclei. About 380,000 years after the Big Bang, the universe cooled enough for atoms, hydrogen, and helium to form, allowing light to travel freely and creating our cosmic microwave background radiation. This cosmic microwave background is crucial evidence for the Big Bang theory. It is mainly after the heat from the Big Bang that we can detect the uniform radiation that permeates the universe today. In addition, the distribution and abundance of light elements observed throughout the universe is consistent with the predictions of the Big Bang nucleosynthesis model, increasing the credibility of the theory. Additionally, the observed expansion of the universe as galaxies move away from us further supports the Big Bang theory. The farther away a galaxy is, the faster it shrinks. The universe is still expanding from an explosive beginning, which can be traced back to cosmic expansion. Reinforcing the idea that everything came from a single event shows that not only space and time, but all matter and energy began. Our universe. The Big Bang theory was first proposed by Belgian priest and astronomer Georges Lemaitre in the early 20th century. In 1927, he proposed that the universe expanded from a point he called the primordial atom, which marked the beginning of everything. Lemaitre's idea for the foundation was based on his understanding of Einstein's theory of general relativity and observations of changes in light from distant galaxies. Although Lemaitre laid the theoretical foundations, it was not until Edwin Hubble made his observations in the 1930s that the concept became more widely accepted. Hubble discovered that galaxies are receding from each other, finding a direct relationship between their distance and the speed of their fall. This observation showed that the universe was indeed expanding, providing significant support for Lemaitre's earlier ideas, now known as the Big Bang theory. The name Big Bang itself was coined by British scientist Fred Hoyle during a 1949 BBC radio broadcast. Hoyle was a proponent of an alternative theory called steady-state theory, which suggested that the universe is eternal and does not change on a large scale. Ironically, by using the term Big Bang, he provided a label that helped popularize Lemaitre's original concept, even as he argued against it. Over time, advances in technology and observations, such as the discovery of the cosmic microwave background radiation and the abundance of light elements, solidified the Big Bang theory as the primary explanation for the origin of the universe. This shared journey of discovery represents the development of scientific understanding through the contributions of many people over the generations. The Big Bang theory is supported by a large body of evidence, with three main pieces standing out. The most important are the cosmic microwave background rays, the heat that fills the universe and is left over from the first moments after the Big Bang. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, This radiation provides a snapshot of the universe as it was 380,000 years old. The uniform distribution and temperature of this radiation closely matches that predicted by the Big Bang theory, suggesting a hot and dense origin. Another convincing evidence is the abundance of light elements such as hydrogen, helium, and lithium. The Big Bang nucleosynthesis model predicts that specific ratios of these elements will be formed in the first few minutes after the initial explosion. When scientists measure the cosmic abundance of these light elements in the universe, they find measurements consistent with Big Bang predictions. This sequence further supports the theory and adds to our understanding of the conditions in the early universe. Furthermore, changes in distant galaxies provide additional support for the Big Bang scenario. Edwin Hubble first showed that galaxies are moving away from us, and the farther away they are, the faster they seem to be moving away. This observation shows that the universe is expanding, a key idea behind the Big Bang theory. This expansion supports the idea that the universe was once very small, hot, and dense, and has since expanded. Finally, the large-scale structure of the universe, including galaxy clusters and cosmic networks, can be explained by simulations based on the Big Bang theory. These simulations show that the universe formed from small changes in density that existed in the early universe, leading to the abundance of galaxies and structures we observe today. Collectively, these lines of evidence provide a solid foundation for the Big Bang theory to explain the origin and subsequent evolution of our universe. According to the Big Bang theory, the universe began about 13.8 billion years ago. This period has been determined by a variety of methods, including observations of the cosmic microwave background radiation, the motion of galaxies, and the understanding of stellar evolution. Each of these aspects provides important information about the timing of events since the creation of the universe. 13. The 8 billion-year estimate comes primarily from detailed measurements of the cosmic microwave background radiation, particularly those collected by missions such as the Wilkinson Microwave Anisotropy Survey and the Planck satellite. By analyzing small changes in air temperature, scientists can estimate the age of the universe because these changes indicate the time when the universe was exposed to radiation, about 380,000 years after the Big Bang. Additionally, this estimate is supported by studies of distant galaxies and their redshifts. Some galaxies are observed to be moving away from us at great speeds, so their distances can be used to calculate how much time has passed since the universe began to expand. The Hubble constant plays an important role in this calculation, allowing astronomers to understand the expansion rate of the universe, which also corresponds to the number of 13.8 billion years. Another method involves examining the oldest stars in our galaxy, the Milky Way. By determining ages using various techniques, scientists can provide a minimum age for the universe by providing a consistent figure from observations of the cosmic microwave background. Together, these various lines of evidence conclude that the universe was indeed 13.8 billion years old, representing a remarkable journey from the fiery beginnings of space to the vast, structured universe we observe today. Just after the Big Bang, the universe was incredibly hot and dense. It was a singularity where all matter, energy, the fabric of space and time, was concentrated into an infinitesimal point. In those early moments, the temperature rose to unimaginable levels, reaching trillions of degrees. This extreme environment was very hostile to normal matter because the particles collided with great energy, resulting in a chaotic gray matter of fundamental particles such as quarks and electrons. During this early stage, known as the Planck age, the laws of physics began to emerge as we began to understand them. It lasted about 10 minutes for minuscule time, up to a power of -43 seconds, after which the universe began to expand rapidly in a process known as cosmic inflation. This inflation removed disorder and caused the universe to cool rapidly, allowing simple particles to form. As the expansion continued, quarks combined to form protons and neutrons, which led to the formation of nuclei. During the first few minutes, known as the nucleosynthesis period, protons and neutrons combined to form hydrogen and helium nuclei. This process produced most of the light-emitting diodes we see today and traces of lithium. During this time, the universe was not open because photons could not travel freely through the dense plasma of particles. Finally, about 380,000 years after the Big Bang, the universe cooled enough for electrons to fuse with these nuclei, creating neutral atoms. This transition marked the end of the recombination period, allowing light to travel freely for the first time. Emission of the cosmic microwave background radiation, effectively illuminating the universe and marking an important event in its evolution. From this initial chaotic state, the universe began its journey to the structured space we observe today. The cosmic microwave background is one of the strongest pieces of evidence supporting the Big Bang theory. This faint glow fills the universe and represents relic radiation from the first moments after the Big Bang. As the universe began to expand, it was a plasma of hot and dense particles that prevented light from traveling freely. As the universe expanded and cooled, about 380,000 years after the Big Bang, atoms could have formed. At this point, the photons finally escape, leading to what we call the decoupling of matter and radiation. The radiation emitted at that time was in the form of electromagnetic waves. Initially, this light was very hot and energetic, but as the universe continued to expand over billions of years, it stretched and cooled, becoming the microwave range of the electromagnetic spectrum. Today, we find this radiation to be a background temperature of about 2.7 degrees Kelvin. This consistency in the sky strongly supports the idea that the universe originated from a hot and dense state. The properties of the cosmic microwave background also match those predicted by the Big Bang theory. Small changes in temperature, detected across the sky, indicate little change in density in the early universe. These changes eventually gave rise to the large-scale structures we observe, such as galaxies and galaxy clusters. By studying these patterns of variability, scientists can glean information about the universe's expansion rate, composition, and overall geometry. In addition, the cosmic microwave background serves as a powerful tool for cosmologists to validate models of the evolution of the universe. Observations from missions such as the Wilkinson Microwave Anisotropic Probe and the Planck satellite have provided precise measurements of this radiation. The obtained data confirm the predictions of the Big Bang theory about the age of the universe, the rate of expansion, and the proportions of the various elements formed in the process of nucleosynthesis. In this way, the cosmic microwave background rays are a remarkable testimony to the origin of the universe and the basic principles described by the Big Bang theory. Cosmic inflation is a theory that proposes a rapid exponential expansion of the universe that occurred after the Big Bang during a small period of 1 second known as the Planck epoch. According to this concept, the universe expanded from subatomic scales to galaxy sizes in a billionth of a second. This rapid inflation helps explain several key observations about the universe that the original Big Bang theory alone cannot adequately address. One of the most important consequences of cosmic inflation is its ability to account for the uniformity of the cosmic microwave background radiation. Without inflation, regions of the universe that are now so far apart would not be in contact with each other, making it difficult to explain why the temperature and pattern of this radiation is consistent across the sky. Inflation suggests that these large regions were very close to each other before expansion, allowing them to equilibrate in temperature and properties. Another remarkable result of inflation is the explanation it provides for the larger structure of the universe. During inflation, small quantum fluctuations were extended to cosmic scales, causing density fluctuations that eventually formed galaxies and large cosmic structures. This process provides a natural mechanism for the chaos we observe today, arising from an initial unity. Furthermore, cosmic inflation may be a flat universe, with a specific geometry governed by the density of matter and energy. Observations, particularly of the cosmic microwave background, supported the idea of a flat universe consistent with inflationary models. This theory also provides a strong explanation for the observed cosmic acceleration in recent years, suggesting that the scalar fields that drive inflation may still be influencing the expansion of the universe. Overall, cosmic inflation enriches our understanding of the early universe by providing a framework for resolving the uniformity of the cosmic background radiation, large-scale structures, and the geometry of the universe, thereby increasing the explanatory power of the Big Bang theory. The abundance of light elements in the universe, particularly hydrogen, helium, and lithium, provides significant support for the Big Bang theory through a process known as Big Bang nucleosynthesis. This theory posits that the extreme temperature and pressure conditions in the first minutes after the Big Bang allowed these light elements to form. As the universe expanded and cooled, protons and neutrons were able to combine to form nuclei. According to predictions from the Big Bang nucleosynthesis model, the normal matter in the universe should be about 75% hydrogen, 25% helium, and contain amounts of lithium and deuterium. Observations of the basic abundances of these elements in space are consistent with these predictions. For example, the comparisons of helium with hydrogen align well with the Big Bang theory, supporting the idea that the early universe produced these elements in a stage of nucleosynthesis. The measured abundances of these light elements provide information about the conditions of the early universe. When astronomers study the composition of old stars and gas clouds, they find that the relative proportions of these elements match the predictions of the Big Bang theory. The uniform distribution of light elements throughout the universe suggests that they were formed by the same processes that occurred in the early universe, further confirming a cosmic origin. Furthermore, the study of these light elements extends beyond their abundance. The presence and distribution of deuterium and lithium provide additional evidence that their abundance may help improve our understanding of the expansion rate and density of the universe. Discrepancies in observations and predictions may challenge our models, requiring further research and refinement of the Big Bang theory. Collectively, the observed abundance of light elements strongly supports the Big Bang theory, suggesting a clear connection between the early universe and the cosmic chemical landscape. When scientists place zero in the context of the Big Bang, they are describing the moment when we understand it began. This point represents the beginning of the universe, when all matter, energy, and the fabric of space and time were concentrated in a very hot and dense state. The symbol T stands for the limit, equal to zero, conditions and events that our current understanding of physics cannot accurately explain because the laws of physics break down under such extreme conditions. When T is zero, the universe is considered not only to be at high temperature and density, but also to have all the fundamental forces of nature, gravity, electromagnetism, and nuclear forces in a unified state. As the universe began to expand from this initial unity, it underwent major changes, leading to the cooling and separation of forces we observe today. This marks the beginning of the evolution of the universe, which eventually gave rise to the structures, galaxies, and cosmic processes we see. It should be noted that the discussion around T is zero, indicating the limits of our current understanding, rather than the precise moment at which our experiments can be investigated. This concept is counterintuitive because we cannot talk about the time before the Big Bang, because time itself began. T is equal to 0 in the early evolution of the universe, setting the stage for events such as cosmic inflation, nucleosynthesis, and the later formation of atoms and galaxies. The phraseology also reflects the complexity of cosmology, as scientists try to piece together the history of the universe from this enigmatic point. Although much remains to be learned about the beginning of the universe, T equal to 0 serves as an important starting point for understanding the evolution of everything we observe in space today. The question of what happened before the Big Bang is deep and complex because it touches on areas limited by current scientific understanding and the conceptual framework of time and space. According to the Big Bang theory, the universe began around 13.8 billion years ago from a very hot and dense state, commonly referred to as singularity. At this point, time and space as we know them came into existence, complicating the discussion of what preceded the Big Bang. In the context of modern physics, time is so closely intertwined with the fabric of space-time that the concept of time may have had no meaning before the Big Bang. Because all dimensions, including time, were created during this event, thinking about what came before can lead to paradoxes or questions that do not have a solid foundation in our current scientific models. That said, many cosmologists believe that talking about before the Big Bang might be a bad question because it implies a time that didn't exist. However, some speculative theories take into account concepts that go beyond the traditional Big Bang framework. For example, some models suggest that the universe undergoes cycles of expansion and contraction, and that our universe is just one of many, perhaps after a previous cosmic phase. Line theory and other advanced frameworks also suggest the possibility of multimedia, or alternate dimensions where different physical laws can be applied. However, these ideas remain theoretical and are not widely accepted in the scientific community. Although there are interesting hypotheses, the limitations of current observational methods mean that we cannot know exactly what happened before the Big Bang. Exploring these concepts invites continuous investigation and debate, pushing the boundaries of our understanding of time, space, and the nature of the universe. At present, the concept of the conditions before the Big Bang remains an open question, pointing to deep mysteries that lie ahead in the study of cosmology. Eternal inflation is a theory that expands the concept of cosmic inflation, suggesting that inflation may be continuous in different regions of space-time, not just in the early universe. According to this idea, even though our observable universe underwent a brief expansion immediately after the Big Bang, there are parts of the universe where inflation continues indefinitely. This creates an infinite number of possible universes from the ongoing inflationary process. In the eternal inflation model, the inflation phase is governed by a scalar field, often called the inflaton. This field can exist in different states, leading to regions with a certain potential energy, causing rapid expansion, while other regions cool and stop inflation. As a result, parts of the universe that reach lower energy states can grow into what we understand as the universe, while inflation continues in the hotter and denser regions. This unique process suggests that new universes can form continuously, resulting in a multiverse, a collection of many universes, each with different physical laws and properties. One of the interesting consequences of eternal inflation is that it may help explain some of the properties of our universe, such as isotropy and homogeneity. Because inflation extends small quantum fluctuations to cosmic scales, the random changes that occurred during inflation set the initial conditions for structure to form in our universe. However, within the framework of eternal inflation, such changes are infinite, creating a vast landscape of different universes with different characteristics. Although the concept of eternal inflation offers interesting possibilities, It also poses challenges for scientific investigation. The idea that our universe is just one among countless others makes it difficult to directly test or observe other universes. Hence, perpetual inflation remains a theoretical construct, providing valuable information about the vast nature of reality and the conditions of space. Continued research and advances in cosmological observations will be crucial in exploring the consequences of eternal inflation and understanding its impact on our understanding of the origin of the universe. The idea of a cyclic universe offers an alternative view of cosmic evolution, opposing the conventional Big Bang theory, which proposes that the universe undergoes an infinite series of expansions and contractions. In this model, instead of a single initial event in which the universe was created, space undergoes multiple stages of expansion, contraction, and collapse. Each cycle begins with a Big Bang-like event, followed by an expansion, then a gradual deceleration, and finally, a contraction, which leads to the Big Bang. This collision, the restart of the cycle, can end up in conditions similar to the initial state of the singularity. The Big Cycle Theory. One of the main problems that the Big Bang model poses concerns its nature of time and the universe itself. The Big Bang theory suggests about 13 points for the universe. 8 billion years ago, cycle model shows that the universe is eternal. This perspective raises fundamental questions about matter, energy, and the fundamental laws of physics, suggesting that the current state of the universe is not a one-off, but a stage in an ongoing cycle. Additionally, the cyclical universe introduces the idea that conditions can change. For example, subsequent cycles may differ in terms of physical constants or fundamental forces, leading to the possibility of completely different universes emerging through each cycle. This variation may also provide explanations for some of the phenomena observed in our universe, such as the homogeneity and isotropy seen in the cosmic microwave background. The laws governing the transition between cycles may be affected. Although the cycle model of the universe is provocative and offers potential solutions to some of the conceptual problems posed by the Big Bang theory, it remains largely speculative. There are significant scientific hurdles to overcome, particularly in demonstrating the mechanisms of the expansion to contraction transition, and in understanding how events such as the Big Bang can lead to new Big Bangs without fundamental changes in the laws of physics. As a result, although the cyclic universe theory offers an interesting line of inquiry, it remains a topic of debate among cosmologists and physicists as they explore the complexities of the universe's past, present, and future. The Big Bounce theory is a cosmological model that suggests that the universe is expanding and contracting rather than from a single event called the Big Bang. According to this concept, instead of starting exactly from unity, the universe returns from a previous phase of contraction to a new phase of expansion. The idea is that the universe may be cyclical, repeating the leap over time without a definite origin. The Big Bounce is based on a modification of classical general relativity that includes the effects of quantum gravity, which allows scientists to describe cases where the density is extremely high, such as what happened during the collapse of the universe. In this framework, instead of reaching infinite density and singularity, the universe passes through a quantum phase in which the laws of physics change. This transition allows you to return to the universe. It leads to a new phase of expansion similar to that described by the Big Bang theory. One of the advantages of the Big Bounce theory is that it solves some of the paradoxes associated with the Big Bang. For example, the singularity at the beginning of the Big Bang raises questions about what conditions must have existed before this event. The Big Bounce concept implies that the universe did not have a single origin, which allows cosmologists to study the continuous evolution of the universe without describing the initial state. Although the Big Bounce theory provides an interesting alternative perspective, it also faces problems. how the transition from contraction to expansion occurs, and what governs this process requires further theoretical development and empirical investigation. Furthermore, while some forms of the Big Bang can make observable predictions, connecting them to measurements and observations of the current universe remains a difficult task. Overall, the Big Bounce theory opens up new ways to understand the past and future of the universe, and provides an interesting perspective on cosmic evolution that contrasts with the traditional view of the Big Bang theory. As research continues, scientists will examine the implications of this model and look for evidence to support or refute its claims. The line theory seeks to explain the origin of the universe by suggesting that the basic building blocks of space are not point-like particles, but small, oscillating lines. These strings can be closed loops or open loops, and their different modes of vibration correspond to different particles such as quarks and electrons. By framing the universe in this way, the Ni theory provides a framework that combines quantum mechanics with general relativity, potentially answering some of the most fundamental questions about the origin of the universe. One of the important consequences of line theory is that it introduces the idea of additional dimensions beyond the familiar one-dimensional space and one-dimensional time. Although our everyday experiences are limited to 4 dimensions, line theory suggests that there are additional dimensions that help integrate the fundamental forces of nature. These extra dimensions may also play a role in the creation of the universe, as their conditions may affect the lines and fundamental forces at the beginning of the universe. String theory also provides a potential mechanism for the dynamics of the universe. This landscape represents a multiplicity of physical dimensions that emerge from different ways of configuring additional dimensions. In this context, the universe we observe may arise from a specific configuration of these dimensions and lines, leading to a unique set of physical laws. This landscape presents a broader picture that includes not only the creation of our universe, but also the potential for other universes with different characteristics in the multiverse. Additionally, some theoretical models include ideas such as brains and high-dimensional objects. Brain interactions can create conditions reminiscent of the Big Bang, where collisions or mergers of brains can trigger the rapid expansion of the universe. Such an event could be similar to inflation and could lead to configurations that mirror those observed in the present universe. Although string theory offers an impressive framework for understanding the origin of the universe, it remains theoretical and faces significant challenges. It is worth noting that many predictions do not need direct experimental verification due to the very small scale of the lines, which are beyond the current technological capabilities. As research continues, scientists are working to study the predictions of the Ni theory, with the goal of finding empirical evidence that can support its claims and better explain the origins of the cosmos. The concept of the multiverse suggests that our universe is one of potentially countless universes that exist simultaneously. Each of these universes may have different properties, laws of physics, and even aspects of reality. The idea is to expand our understanding of the cosmos beyond the framework of the one universe most of us know. Different theories propose different types of multiplicity, some stemming from quantum mechanics and others related to cosmic inflation, which rapidly expanded the universe after the Big Bang. The big explosion happened around 1300 hours. 8 billion years ago defines the origin of our universe as we know it. This event created space, time, matter, and energy all at once. The connection between the Big Bang and the multiverse concept arises primarily from certain cosmological models, particularly those that suggest that our universe is a bubble within a larger bubble of universes. When the expansion began, some regions of space rose faster than others, creating separate bridge-like universes disconnected from each other for no reason. According to some theories, as our universe expands, Other cosmoses may form where voids can form. These alternate universes may operate under different physical laws, leading to profound differences, such as different constants of nature and even different dimensions. The implications of this are far-reaching, suggesting that there may be universes where different forms of life have evolved, or where the laws of physics are different enough to create a completely different reality. When scientists study these ideas, they enter into the nature of reality. The multiverse theory raises philosophical questions about the uniqueness of our universe and points to a fundamental structure that connects all of existence. Although evidence for multimedia remains elusive, research in cosmology and physics continues to expand our understanding, sparking excitement and speculation in the scientific community. Quantum fluctuations are temporal changes in the amount of energy present at a point in space, as predicted by quantum mechanics. These fluctuations are caused by the uncertainty inherent in energy levels at the quantum scale. For example, Heisenberg's uncertainty principle states that the more precisely we know the energy of a system, the more precisely we can know its position, and vice versa. This interaction creates an environment where energy is generated spontaneously. A stellar flare called RS Serpentor has erupted 4,500 light-years away in the constellation Serpent. This flame was so bright that it can now be seen with the naked eye. Its magnitude is about 4.8, a full 7 magnitudes brighter than normal. New stars are rare, but RS Serpens is an even more interesting case. This is because the cataclysmic variable star that flares up from time to time in front of us, and there are only 10 such stars in the Milky Way. Snake's RS has a flame periodicity of about 15 years, a white quartet in close orbit with a red giant. As they orbit each other, gas, primarily hydrogen, is ejected from the red giant by the white dwarf, which is smaller and denser. This hydrogen then collects on the surface of the white dwarf, where it is heated. Occasionally, its mass becomes so great that the pressure and temperature below cause a thermometric explosion, ejecting excess matter into space at a speed of 2,600 kilometers per second. If the white dwarf accumulates so much mass that it exceeds a critical threshold, it will become unstable and explode in a supernova. This snake may also happen with MS, but for now the two stars continue to live in close orbits. After a quick flash over the next few weeks, serpentine MS will gradually fade and eventually disappear. The next discovery will be only in 15 years, so astronomers advise not to delay the observations. The constellation Serpent is visible to the south. It is not very bright, so it is recommended to look for a new one in the backlight, not in the city. Remember and have a good hunt. The Milky Way galaxy is a medium-sized galaxy. This galactic island may have as many as 100 billion planets. It should be noted that most of them have not yet been studied. Exploring our galaxy will probably take hundreds, if not thousands of years from our apartment closet. And yet, each of the exoplanets confirmed by astronomers has unique features and characteristics, sometimes radically different from what you and I see. This uniqueness can manifest itself in many ways. Today we're going to tell you about two interesting exoplanets that not only orbit their closest parent star, but eventually become something more. In our solar system, the closest planet to our star is Mercury, the smallest of the terrestrial planets. It moves at a speed of 47 kilometers per second at a distance of 58 million kilometers from the Sun. However, it is far from the record holder in terms of speed and proximity to the parent star. The name now boasts a very large Jupiter-class planet. TOI 2109b orbits a star in a star system located 855 light-years away, with a record low orbital period. It takes only 16 hours to complete its orbit. Come to think of it, you're not out of date yet. And it's New Year's Eve on planet Toei 2109b, and even though the Christmas tree is lit, there doesn't seem to be anyone there to celebrate. Because the daytime temperature is about 3,225 degrees, which is almost the temperature of small stars, so there is no such thing as light tan. TOI 2109b is about 2. At 4 million miles from its star, the gas giant is in tidal lock, and because of its close proximity to the planet star, the TOI 2109 system is an ideal laboratory. Study of planetary wave breaking by the gravitational pull of stars. Planets close to their stars that are still on the main sequence in the Hertzsprung-Russell scheme, that is, have thermometric reactions of hydrogen to helium fusion in their cores. What does this mean? Consider the following example. According to modern representatives, white swans may have companion planets. Until recently, a direct indication of this was not known. But recently, in the constellation Dragon, 80 light-years away from us, an unusual white dwarf whose companion is regularly eclipsed was discovered. It blocks most of the light that reaches the bush from the ground. According to the researchers, this companion could be a planet of the type and size of Jupiter, or, less likely, a brown dwarf. These observations were also supported by data from the Spitzer Space Infrared Telescope. The collected data allowed us to determine with complete confidence that WD 1856-534, a transiting white dwarf companion of Jupiter. On its own, this doll is nothing special. With a temperature of 4,500 degrees Celsius, it is cooler than the Sun. This means that it formed about 6 billion years ago, long before the formation of the solar system, and has had some time to cool down since then. It has about half the mass of the Sun, and its radius is 75 times smaller than that of the Sun, or 40% larger than that of Earth. Of course, it is not simple in the sense that it is an external component of the visual three-star system. Internal components. The white dwarf companion, designated WD1856b, has a large semi-major ellipse with a length of 0.02 solar units. In other words, it is 3 million miles from its star, which is 20 times smaller than the average orbital radius of Mercury mentioned above. The radius of this body is more than 10 times that of Earth. Thus, compared to the star WD 1856-534, the object looks like a true giant. This explains the strong conservation of dwarf light that the researchers found. WD 1856b is known to have an orbital period of only 34 hours around the white quaternary. Unfortunately, the exact mass of the satellite planet is still unknown. To determine its radius, we need to know its radial velocity, which has not yet been determined. This velocity is measured by the Doppler shift of the spectral lines, which are not visible in this case. Nevertheless, we still learn something interesting when we compare the results of light conservation observations made with the giant telescope photometers on the island of La Palma with similar observations in the near-infrared region, with equipment, Spitzer telescope. Thus, the dynamics of light changes in both ranges turned out to be almost the same. After that, the exoplanet's thermal radiation flux is no more than 6% of the dwarf flux. That is, such a dark body could be a giant planet, or a very low-mass brown dwarf. Recent analysis suggests that the mass of WD 1856b should not exceed 13.8 Jupiter masses. This estimate is almost equal to, but slightly below, the theoretical low associated with the mass of brown bushes, so selection in their favor is unlikely. Based on the available information, we can confirm that we are talking about an incredibly large planet. But as a companion, WD 1856b could be 3 million miles away from the white dwarf. and how it may have escaped the star's death. The fact is that in the process of becoming a red giant, the star absorbs its planets very closely. The Sun will destroy Mercury, Venus, and possibly Earth in about 5 billion years. But how did planet WD-1856b survive? Because in its current orbit, it would have burned up long ago. The researchers suggest two plausible scenarios to consider. First, White Darvish's star was originally supposed to be a red giant before it died, blossoming with an ego the size of Earth's orbit. If a planet is at short distance, it would have been completely enveloped by the giant's outer shell, and if it had been surrounded by hot gas, it would have lost its burnt-out outer layers, but may have retained its inner chambers. Moving in a cloud of gas plasma, it was braked by friction and approached the dense core of the star, after which it threw off gas shells and became a white bush. After jettisoning, the planet was once again in gas-free space, and it entered a stable orbit around the dwarf. If the shedding of the red giant's crust is delayed, the planet will continue to accelerate and eventually collide with the star's core in a catastrophic cataclysm. Astronomers on Earth would not have expected the white owl and its companion to survive. Whether the satellite itself, a planet, or a brown dwarf, was to be completely destroyed. However, this scenario is less likely as model simulations show that it is impossible for the outer shell of the red giant to completely stabilize the satellite's orbit due to the operation of several dynamical mechanisms. Here we come to the second scenario. The same simulations show that the progeny star had multiple planets in distant orbits, and after becoming a red giant, their orbits lost their previous stability. As a result, the planet WD-1856b gradually moved into a trajectory near the dwarf, and the others, if any, were thrown into free flight through space. This restructuring can take about 1 billion years, which corresponds to the age of the white dwarf. It's like what happened, and once the planet was bigger than the star, it orbited. Yes, space is definitely an interesting place, full of interesting and even mysterious phenomena and objects. Well, for a custom James Webb telescope, there's a lot of work ahead, including learning about this amazing couple. I hope that still solves the question about the nature of the WD-1856b output. A mysterious object. However, some supernova explosions are probably not powerful enough to completely destroy nearby stars, like what happened with the LP-4365 White 4. An international team of astronomers has received new information about a mysterious object seen in 2017 dubbed the Runaway star from the hotspots. This space shuttle appears to have traveled the entire Milky Way at a speed of about 3.5 million kilometers per hour. And it's moving in the wrong direction, where most of the stars are in the center of our galaxy. Another anomaly was discovered. This object is made of a completely different material than the rest of the stars in the Milky Way. It is filled with heavy metal atoms, while other stars are dominated by light chemical elements. The incredible speed of movement suggests that the object is trying to leave the boundaries of our galaxy. Based on this fact, astronomers have proposed in a new study that such a speed could develop a celestial body that survived a violent cosmic catastrophe. It has been suspected that a supernova explosion resulting in a powerful release of energy could give the star a massive boost. This is quite possible if the object is part of a binary star system consisting of a pair of white dwarfs. The fate of such small but powerful stars is typical. Over time, one star drains so much mass and energy from its vampire-like partner that it eventually explodes. Such explosions are so powerful that they fuse the cores of old elements into completely new elements, then shoot the star in any direction. Now a new traveler with no orbit and no satellites is speeding toward the edge of our galaxy. What happens after that? Will he be able to leave the galaxy or return? We no longer recognize it. Chemical elements are the basic identifying forms of the material world. The periodic table of chemical elements is considered one of the greatest achievements of chemistry. Today, it is considered almost twice as much as it was half a year ago, when it published Dmitry Ivanovich Mendeleev's experiments on the system of elements based on atomic weights and chemical combinations. As it turns out, this sheet is the reason why our world appeared not only on Earth, but also outside. For example, the chemical composition of the Sun's surface is mostly 74% hydrogen and 24% helium. Their predominance characterizes our stellar nature. Iron, sulfur, magnesium, calcium, oxygen, etc. Elements such as are present in small amounts. Yes, almost all stars are made of gas. If the stars make sense, there is something more mysterious in the universe. For example, black holes. Of course, like the Sun, or a neutron star, most of Mendeleev's table could contain a black hole. But in what form? Black holes are a fantastic phenomenon in space. We don't know much about them. And this raises the question of whether there are elements inherent in cosmic bodies and effects in our universe that humanity does not know about. Today, we will try to understand it in short and convenient language. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light, and thus violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let it be a ball of particles, and the elements can live up to about 173. There may be atoms beyond this limit, but only strange entities that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126, and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments, but also by analyzing the distribution of various elements in nature. By distribution, you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in its nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, the neutron and proton shells in the nucleus are formed. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a superelement with a twice magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, is still unpredictable. Another region of stable isotopes is expected around atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements, as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons, it will be difficult to study them directly, because you can quickly get into a breakdown to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerated and crashed into a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton, and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic, or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom. Because less than 10 trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with great gravity, constant or variable temperature, new elements of matter not only abundantly replenish the table, but can also go to a new level unknown to us. Yes, it is possible that black holes consist of a complete set, or nearly complete set, of primordial particles that decay into energy, perhaps into an indescribably fantastic conglomeration. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states. And these energies and forces of modern physics are known. And here the combination of these energies can create something unknown to science. What would happen if a supernova exploded near Earth? Actually, there are 3 answers, none of which are very comforting. But before we answer them, let's try to understand what a supernova birth is, and why they can harm all life, even if they are very distant. Thus, a supernova, or supernova explosion, occurs when a star rapidly increases in brightness and then collapses relatively slowly. A supernova is observed post facto, that is, after the event and its radiation reaches our keen eyes. A supernova occurs when there is a change in the center or core of a star. The change can take two forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is two stars orbiting the same point. One of the stars, white 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, a neutron star, or a black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers, a high density of up to 1 billion tons per cubic centimeter, and 2.5 times the mass of the Sun. After a supernova explosion, two types of neutron stars remain: pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars spin at high speeds on their axis, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, this result is highly probable. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's Betelgeuse, which is 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation Orion continues to amaze with its mysterious behavior. At the end of 2020, it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse due to gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes, sometimes people start doing things when it's too late and after the last star has left the station. And it is better to prepare everything in advance. So if it's Betelgeuse, we shouldn't expect much danger. Yes, the spectacle would be spectacular, but the Earth would not be shaken by the shock wave. The towers of heaven would not fall like staves. The sea would not rise like walls, and the inhabitants would not be kindled by fire. The last day of the apocalypse. I'm sorry, Thanos. So what do we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course, we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night. But it will not be like the second Sun. During the day, Betelgeuse will appear as a large, bright spot, larger than an ordinary star, but smaller than the Sun. At night, Betelgeuse will appear as a large, bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months, or up to a year. For another 2 years, it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will soon be able to see the star's crust. Fact: the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us. The periodic fading of stars in the Crab Nebula is caused primarily by the presence of a neutron star at its center, known as the Crab Pulsar. This pulsar is a strongly magnetized rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the pulsar rotates, these rays spread through space like a lighthouse beam, creating the phenomenon of periodic dimming or pulsation when viewed from Earth. As it rotates, the pulsar produces intense bursts of radiation over a range of wavelengths, including radio, optical, and X-rays. When the beam of radiation is directed toward Earth, the star appears brighter. As the beam spins sideways, the star dims. This periodicity is incredibly precise. The Crab pulsar makes one revolution about every 33 milliseconds. The regularity of this pulsating effect is one of the most interesting characteristics of pulsars, providing important information about the rotation and magnetic field of the stellar remnant. The environment surrounding the pulsar is also significant. The Crab Nebula itself is the result of a supernova explosion that produced a pulsar in 905 AD. The expanding supernova debris interacts with the pulsar's magnetic field, creating a complex structure of shocks and radiation in different wavelength ranges. This interaction generates additional radiation that contributes to the observed brightness changes associated with periodic dimming. Studying the periodic dimming of the Crab Nebula, which is primarily due to pulsar activity, not only deepens our understanding of the life cycle of stars, but also provides insight into the physics of neutron stars and the extreme conditions that exist in their neighborhoods. Pulsars like the Crab Nebula provide a natural laboratory for studying fundamental questions in astrophysics, contributing to our understanding of the behavior of the universe and the life cycles of celestial bodies. The phenomenon of some stars appearing older than the universe itself is a fascinating mystery in astrophysics, arising from various factors related to the formation and measurement of stars. The age of the observable universe is estimated to be about 13.8 billion years old, based on cosmic microwave background radiation and other cosmological data. When astronomers observe certain stars that appear to be older than this time interval, this provides a deeper look at the intricacies of stellar evolution and the difficulties in age estimation. One of the main reasons for these apparent age discrepancies has to do with the methods used to determine the age of a star. Astronomers often estimate stellar age based on a star's position on the Hertzsprung-Russell diagram, where stars are arranged according to their brightness and temperature. However, this method can lead to uncertainties, especially for stars in later stages of evolution. If the star is in a part of the diagram that suggests a much older age, this may not accurately reflect its true age if the underlying assumptions about evolutionary processes are flawed or incomplete. Another factor contributing to this paradox is the nature of the star's composition. Stars with high concentrations of heavy elements, known in astronomy as metals, usually form after previous generations of stars have evolved and died, enriching the interstellar medium. Therefore, a star with low metallicity may indicate that it was born from primordial materials, suggesting that it has existed since the early universe. Nevertheless, stars with lower metallicity may appear older than they actually are because of the complexities of stellar dynamics and life cycles. In addition, some stars are part of globular clusters, which are dense clusters of ancient stars. The age of these clusters is difficult to determine precisely. The oldest globular clusters are estimated to be nearly 14 billion years old based on stellar models, making them seemingly bumping up against the upper limit of the age of the universe. Such a coincidence calls into question the very models we use to estimate stellar ages and star formation histories in the cosmos. In conclusion, the apparent older age of some stars challenges our understanding of stellar evolution and highlights the need for improved modeling techniques. As researchers continue to study these celestial objects with modern telescopes and improved techniques, we can further understand the tangled history of our universe and the stars that inhabit it. Ultra-luminous X-ray sources, commonly referred to as ULXs, are unusual astrophysical phenomena found in various galaxies beyond our planet. They are characterized by incredibly high X-ray luminosity, 1,000,000 times the luminosity of the Sun. ULXs are of great interest to astronomers because they are some of the most intense X-rays observed in the universe and produce emission that often exceeds that generated by typical stellar sources. The exact nature of ULXs remains the subject of active research, but they are generally thought to be associated with binary systems involving a compact object, such as a black hole or neutron star, that accretes matter from a companion star. In particular, many ULX are thought to host black holes with masses ranging from a few to a few tens of solar masses, distinguishing them from the stellar mass black holes commonly found in our galaxy. The accretion process occurs when the matter of a companion star flows into a black hole, generating enormous amounts of energy as the falling material heats up and emits X-rays. Another intriguing possibility is that some ULX may be associated with intermediate mass black holes, which are a missing class of black holes that have masses between 100 and 1,000 solar masses. The detection of intermediate mass black holes in ULXs can shed light on the formation of supermassive black holes at the centers of galaxies, which can have masses millions or even billions of times that of the Sun. In addition, ULX can exhibit brightness variability, indicating a change in accretion rate. Sudden outbursts and fluctuations can provide additional insight into the dynamics between the accreting matter and the compact object. This variability often makes ULX a rich field for studying the fundamental physics of black holes, accretion flows, and the environments in which they exist. The study of superluminous X-ray sources continues to advance with advances in observational technology and observing campaigns in both the optical and X-ray wavelength ranges. As we learn more about these mysterious objects, they open a unique window into the extreme astrophysical processes and interactions between stars and their compact remnants, enriching our understanding of the cosmic landscape. Each discovery adds another layer to the tangled tapestry of the universe and spurs the quest to comprehend the fundamental nature of matter and energy in extreme conditions. The phenomenon of some galaxies having almost no star formation despite an abundance of gas is a fascinating area of research in astrophysics. At first glance, this seems counterintuitive. The presence of large amounts of gas, which is the primary fuel for star formation, should lead to active starbirth. However, various factors can inhibit this process, leading to a condition known as star formation fading. One important reason for this attenuation has to do with the dynamics within the galaxy itself. In some cases, the gas in such galaxies may not be dense or cold enough to collapse into stars. Factors such as turbulence or heating from existing stars can prevent the gas from cooling and condensing, creating a barrier to star formation. For example, in some massive elliptical galaxies, the presence of supermassive black holes at their centers can drive powerful winds or jets that heat the interstellar medium, effectively slowing or stopping the cooling processes necessary for star formation. Moreover, galaxy mergers and interactions can greatly affect the rate of star formation. When galaxies collide, they can direct gas toward their centers, causing bursts of activity. But in other cases, These interactions can cause the gas to be expelled from the galaxy or redistributed in a way that prevents star formation. Gravitational forces can carry the gas away or create conditions that stabilize the gas against collapse into stars. Another factor may be the role of dark matter and the overall gravitational potential of the galaxy. For galaxies in which there is no active star formation, the binding energy of the dark matter halo may not provide the conditions necessary to effectively trap gas. Reduced gas volume resulting from interactions with the environment or from the higher gravitational potential in a galaxy cluster can also remove gas that would otherwise be available for star formation. In addition, the role of the cosmic web cannot be ignored. The large-scale structure of the universe affects the flow and distribution of gas. In some regions, the influx of gas from the intergalactic medium may be suppressed due to the large-scale environment, further limiting the amount of gas available for star formation. Understanding why some galaxies can retain significant amounts of gas without turning it into stars provides critical insights into the evolution of galaxies. By delving deeper into this topic using advanced observational and modeling techniques, researchers aim to unravel the complex interplay of gravitational, hydrodynamic, and chemical processes that have shaped the life of galaxies throughout cosmic history. Each new finding deepens our understanding of galaxy formation and evolution, revealing the complex nature of the universe in which we live. The ripples observed in the Milky Way disk are a remarkable phenomenon that allows us to understand the dynamics of our galaxy. These pulsations are primarily caused by the gravitational interaction of stars within the disk, as well as the influence of nearby structures. One important contributing factor is the passage of spiral arms. As stars and gas clouds move through these arms, they experience a gravitational pull that creates perturbations that result in wave-like shapes in the distribution of stars and gas. In addition, interactions with companion galaxies play a crucial role in creating these ripples. The Milky Way is not an isolated entity. Several small galaxies, such as the Large and Small Magellanic Clouds, orbit nearby. The gravitational attraction of neighboring galaxies can cause tidal forces that affect the distribution of stars in the Milky Way disk. Over astronomical time, these interactions can accumulate and create the observed waves or ripples in the galaxy structure. Another interesting aspect is the potential involvement of dark matter. Although we cannot see dark matter, it is believed to make up a significant portion of the galaxy's mass. Its gravitational influence may also contribute to the movement of stars, resulting in these rippling patterns. This concept allows scientists to study the influence of dark matter indirectly, through the behavior of visible stars. Researchers continue to analyze data from telescopes and other instruments and reveal the complexity of the Milky Way's structure. Understanding these ripples not only helps us understand our own galaxy, but also sheds light on the interactions occurring in other galaxies throughout the universe. Each ripple tells a story of cosmic motion and the gravitational dance between celestial bodies. The intricate and symmetrical shapes of some planetary nebulae result from a complex interplay of processes late in a star's life. When a medium-sized star like our Sun exhausts its nuclear fuel, it undergoes a series of transformations. When the core contracts and heats up, the outer layers of the star are ejected into space, forming a glowing shell of gas and dust known as the planetary nebula. The symmetry often observed in these nebulae can be explained by the dynamics of the ejection process. One of the main factors influencing the shape is the role of magnetic fields. When a star sheds its outer layers, magnetic fields can create organized structures within the ejected material. These fields help direct the flow of gas, resulting in more uniform, complex shapes rather than random distributions. In many cases, these magnetic fields also interact with the stellar wind, a stream of charged particles ejected from the star, reinforcing this ordered structure. In addition, binary star systems contribute significantly to the formation of symmetric shapes. If a star exists in a binary system, interactions between two stars can lead to mass exchange and the formation of ejected material. A single star can shed its outer layers while a companion gravity attracts and directs this material, creating a more structured and recognizable shape. This gravitational interaction can lead to the formation of jets and lobes that produce the unique and often beautiful shapes we observe. The combination of these processes creates the breathtaking patterns observed in planetary nebulae, which can range from circular and spherical to more complex shapes, including intricate knots and filaments. Studying these structures not only deepens our understanding of stellar evolution, but also provides clues about the physical conditions late in the life of a star. Each planetary nebula is a snapshot of cosmic processes, demonstrating nature's mastery of the universe. The interstellar object known as Oumuamua has intrigued scientists since its discovery in 2017, providing a unique opportunity to study a visitor from outside our solar system. Oumuamua is believed to have a rocky or metallic composition, and its unusual shape is elongated and cigar-shaped, which is very different from typical asteroids or comets found in our solar system. The name Oumuamua comes from the Hawaiian language and means scout or messenger, which is quite reflective of its status as the first detected interstellar object to pass through our planetary neighborhood. Scientists hypothesize that Oumuamua originated from a star system beyond our planet, as a result of an ejection from its home galaxy. This ejection could have been caused by gravitational interactions with other stars, which could have caused it to be flung away at high speed. Freed from its original star system, Oumuamua traveled the vastness of space for millions of years, eventually making its way to the inner solar system, where we discovered it. Another intriguing aspect of Oumuamua's journey is its trajectory. As it traveled through the solar system, the object exhibited unusual acceleration, which some scientists initially attributed to outgassing, a common phenomenon observed in comets. However, the lack of a visible comet-like tail led researchers to consider alternative explanations, including the possibility that it was a fragment of a larger body, or perhaps playing some role in the complex dance of interstellar dynamics. Ultimately, Oumuamua serves as both a scientific mystery and a reminder of the dynamic nature of the cosmos. Its presence raises fundamental questions about the distribution of interstellar objects and the processes that govern their movement through space. Through continued research and observations, scientists hope to learn more about the origin and properties of such guests, leading to a deeper understanding of the universe beyond our solar system. The presence in some star clusters of several populations of stars with different compositions provides a glimpse into the complex history of these celestial formations. In particular, the phenomenon is most prominent in globular clusters, ancient groups of stars orbiting galaxies. The different populations can be attributed to the environment in which the clusters formed and the subsequent evolutionary processes through which they passed. One of the main reasons for the multiplicity of populations is the initial conditions of cluster formation. Many star clusters formed in dense regions of gas and dust, where the first generation of stars created heavy elements through nuclear fusion. When these stars reached the end of their life cycle, they enriched the surrounding matter with heavier elements, a process called metallicity. The enriched gas subsequently became the raw material for the next generation of stars, giving rise to a second population with a different composition, often exhibiting higher metallicity than the first. In addition, the diversity of stellar populations can be facilitated by interactions between stars within a cluster. As stars evolve, some of them may eject material that can be accreted by younger stars, further changing their chemical composition. It is also hypothesized that in some clusters, periods of star formation extended over millions of years. These intervals allowed different compositions to form as the stellar environment evolved. Moreover, in some cases, the detection of multiple populations challenges previous ideas about how star clusters evolve. The idea that globular clusters may have formed from the merger of smaller clusters suggests that what we see today is a mixture of different star formation sharing space in the gravitational capture of the cluster. This complex interplay of formation history and stellar evolution makes the study of star clusters particularly fascinating because they reveal the processes that shape the universe on vast scales. Each cluster contains a wealth of information about the life cycle of stars and the chemical evolution of galaxies. The periodic brightening of the Blazar OJ 287 is a surprising phenomenon that has attracted the attention of astronomers for several decades. Blazars are a class of active galactic nuclei characterized by powerful jets of relativistic particles pointed almost directly at Earth. These jets emit radiation throughout the electromagnetic spectrum, and OJ 287 is particularly notable for its brightness fluctuations, which occur about every 12 years. The periodic activity observed in OJ 287 is explained by the interaction of a supermassive black hole at the center of the galaxy with another black hole. This system consists of a primary black hole actively accreting matter, surrounded by a secondary black hole in a binary system. When a companion black hole orbits around a larger black hole, it exerts a gravitational influence on the material of the accretion disk surrounding the main black hole. This gravitational influence can enhance the accretion process, resulting in increased radiative power as the companion black hole approaches. During periods of increased activity, the energy released as matter spirals into the black hole increases significantly. This outburst leads to a sharp increase in the brightness of the blazar, causing the flares observed from Earth. The mechanism of these flares may also involve a complex interaction of shock waves propagating down the jet, further enhancing the brightness through the Doppler effect as the material travels at close to the speed of light. The cyclicity of OJ 287 strengthens the understanding of black hole interactions in active galactic nuclei. Observations of its amplification not only provide insight into the behavior of matter under extreme conditions, but also help improve our knowledge of the dynamics of such massive systems. OJ 287 serves as a critical source of information in the quest to comprehend the workings of the universe at its most energetic and fundamental levels. Binary systems often go through a stage known as common envelope evolution, which can significantly change their structure. This occurs when one of the stars in a binary expands into a giant star, enveloping the other star in a shared outer layer of gas. Gravitational interactions between two stars can cause an abrupt transformation of their orbits and potentially lead to the ejection of the outer shell. However, some binary systems manage to survive the common shell phase, and this resilience can be explained by several key factors. One important factor is the ratio between the masses of the two stars. If the secondary star is massive enough, it can help stabilize the common envelope phase by retaining some of the material ejected from the primary star. Eventually, this containment may allow the two stars to continue interacting, facilitating additional mass transfer and allowing them to remain bound together. The interaction with the secondary star also helps dissipate energy, which can prevent the envelope from dissipating too much, allowing the binary system to evolve successfully. In addition, the dynamics of the common envelope itself plays a significant role in the outcome. During this phase, stars can undergo dramatic changes, including a rapid decrease in orbital distance. If the energy released when the primary star's envelope collapses into the companion core is enough to completely expel the common envelope, the evolutionary path may lead to a closer binary configuration. A closer orbit could bring the two stars closer together, increasing the rate at which they interact and setting the stage for future evolution. The presence of additional factors, such as the spin and rotation of the stars, can also affect the ability of a binary system to undergo common envelope evolution. The orientation of the star's spins and their magnetic fields can affect the physics of the shell dynamics, thereby influencing whether or not the binary system can survive. In cases where the stars are favorably located, this interaction can help the system maintain its integrity and prevent it from completely collapsing. These mechanisms demonstrate that binary systems are capable of a variety of evolutionary pathways that allow them to adapt and survive even after intense transformations. Understanding how these systems cope with such transitions provides insight into the complex life cycles of stars and the intricate relationships that can form in the cosmos. Each binary system offers a unique story about stellar evolution and the diverse outcomes that can result from the interaction of massive objects in space. Dark flow is a phenomenon observed in cosmology, which means an unexpected large-scale motion of galaxy clusters in a certain direction. This peculiar motion was first discovered through measurements of the cosmic microwave background radiation, particularly when studying the motion of clusters away from the mean distribution predicted by the Standard Model of cosmology. The observed motion suggests that these clusters are not simply expanding uniformly, but are under the influence of gravitational attraction from unseen structures outside our observable universe. One potential explanation for dark flow points to the existence of massive structures lying beyond our observable boundaries. These structures may include huge galaxy clusters or superclusters that emit gravitational forces strong enough to affect the motion of nearby galaxy clusters. Because these regions are off-limits, they remain hidden from direct observation, so the gravitational influence we detect through dark flow is a critical clue indicating their existence. The implications of dark flow also extend to the theory of the multiverse. If dark flow indicates the existence of structures outside our observable universe, this raises profound questions about the structure and nature of these regions. Some theories suggest that these unseen influences may even communicate with other universes, suggesting a shared cosmic environment with different characteristics, densities, or principles of physics. Such interactions could potentially explain the observed large-scale motions and lead to a better understanding of the overall topology of the cosmos. The study of dark flow offers both exciting opportunities and major challenges for astronomers. It emphasizes the need for more research into the large-scale structure of the universe and the gravitational dynamics governing galaxy clusters. As we improve our techniques and collect more data, dark flow may reveal crucial information about the cosmic landscape, possibly leading to a better understanding of the nature of the universe and the mysterious structures that lie beyond our horizons. Large-scale structures, such as filaments and walls of galaxies, play a crucial role in our understanding of the universe, especially with respect to the boundaries of our observable universe. These structures form a vast, tangled cosmic web of matter, including galaxies and dark matter, bound together by gravity. They arise from the gravitational pull of matter over billions of years, resulting in regions of increased density where galaxies cluster together while vast voids remain largely empty. Understanding how these structures relate to the boundaries of our observable universe provides insight into the overall architecture and evolution of the cosmos. Within the universe we observe, galaxies are the threads of this cosmic web, creating vast elongated structures that can span hundreds of millions of light-years. Filaments connect galaxy clusters, forming a network that delineates the distribution of cosmic matter. On the other hand, walls are larger, flat structures that represent the densest regions of the cosmic web, with clusters of galaxies clustered on their surfaces. By studying these large-scale structures, we reveal crucial details about the formation of galaxies and the distribution of dark matter that governs the evolution of the universe. The distribution of these structures also presents a unique relationship to the boundaries of our observable universe. When we look farther out into space, we observe regions that are less affected by large-scale structures because of the constraints of light travel time. The observable universe is limited to what we can detect within the spherical volume that has been expanding outward since the Big Bang, meaning that some large-scale structures may exist beyond our observational reach. This limitation creates a scenario in which only certain parts of the cosmic web are visible. leaving other potential filaments and walls inaccessible to direct observation. Understanding large-scale structures also helps us theorize about the universe as a whole and about regions beyond our observable boundaries. The regularities observed within our universe may provide clues about the overall topology of the universe and how structures may be organized in regions we cannot currently see. This relationship suggests the existence of similar or completely different structures in the unobservable universe. This leads to intriguing possibilities about the nature of reality and the interconnectedness of cosmic bodies in the cosmos. As observational techniques advance, we will be able to expand our understanding of large-scale structures, bringing us closer to understanding the full scale of the universe and what lies beyond our visibility. The axis of evil in cosmology refers to an unexpected alignment observed in the cosmic microwave background radiation data. Originally discovered by scientists analyzing ring structures in the cosmic microwave background, this alignment suggests that some large-scale features in the universe have a directional gradient. In particular, this axis seems to point to a region in the sky, raising questions about the isotropy of the cosmos. The principle that the universe should look the same in all directions when averaged over large scales. This discovery has significant implications for our understanding of cosmic isotropy because it challenges the standard cosmological model that assumes a homogeneous and isotropic universe. If the universe is truly isotropic, then the cosmic microwave background radiation should exhibit constant properties regardless of the direction of observation. However, the alignment of temperature fluctuations and the orientation of large-scale structures on the axis of evil hints at an underlying asymmetry that contradicts the predictions of the isotropic model. There are various explanations for this phenomenon. Some scientists speculate that the axis of evil may be the result of statistical anomalies or foreground contamination in our own galaxy affecting observational results. On the other hand, it may mean that there are cosmic structures or influences yet to be discovered, including potential interactions with regions outside our observable universe that affect these dimensions. If the axis of evil is indeed a genuine feature of the universe, this may mean that our understanding of cosmic expansion, structure formation, and the general nature of the cosmos needs to be re-evaluated. The implications of this could extend far into the realm of fundamental physics, affecting our understanding of dark energy and other cosmological components, or even hinting at a multiverse theory in which local anisotropies may arise from interactions with other universes. The study of the axis of evil continues to stimulate scientific dialogue and research. As researchers collect more data and improve measurement techniques, we may be able to gain deeper insights that will either confirm or refute existing cosmological models. Ultimately, these studies could lead to breakthroughs in our understanding of the structure and dynamics of the universe, as well as the fundamental principles governing its behavior. Gravitational waves are ripples in the fabric of space-time, resulting from some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. Their detection, primarily by observatories such as the Laser Interferometer Gravitational Wave Observatory, has opened a new window into space, allowing scientists to gather information beyond what can be observed with conventional electromagnetic signals such as light. One of the key ways in which gravitational waves can provide insight into regions beyond our observable universe is their ability to reveal information about cosmic events occurring over vast distances. Because gravitational waves propagate at the speed of light and are less affected by intervening matter than electromagnetic radiation, they can carry information from regions that otherwise remain incomprehensible or unreachable. For example, mergers of black holes or neutron stars that generate gravitational waves could occur in regions of space inaccessible to our observation, allowing us to indirectly study events occurring outside our observable universe. Interestingly, the properties of the gravitational waves we detect can also provide clues about the medium from which they originate. Analyzing the frequency, amplitude, and waveform of these signals could give researchers information about the mass and energy dynamics of colliding bodies. If we were able to detect gravitational waves from events that can be linked to the early universe, such as primordial black holes or inflationary time phenomena, this would deepen our understanding of the conditions shaping the cosmos and allow us to penetrate regions that have since moved beyond what we can see. Moreover, gravitational waves can shed light on the nature and behavior of dark matter and dark energy, components that affect the large-scale structure of the universe but remain elusive to conventional observations. By studying how gravitational waves interact with these objects, researchers will be able to better understand their effects over vast distances, closing gaps in our knowledge of cosmic regions beyond our reach. As detection techniques improve and the science of gravitational wave astronomy advances, there is great potential for discovering new phenomena and gathering information about unseen corners of the universe. This could revolutionize our understanding of cosmic history and the complexities that lie beyond the universe we observe, open up a landscape rich in potential discoveries, and change the way we think about existence in the cosmos. Dark matter plays a crucial and complex role in the structure and dynamics of our universe, and its properties may also shed light on connections to other universes. Dark matter, which makes up about 27% of the total mass energy of the universe, does not interact with electromagnetic forces like ordinary matter, making it invisible and detectable only through gravitational effects. The elusive nature of dark matter means that it may not only influence the behavior and formation of structures within our universe, but also hint at the existence of unseen realities beyond our observable sphere. One possibility is that dark matter may serve as a bridge between universes, especially in the context of multiverse theories. If there are multiple universes with different physical laws or dimensions, then dark matter may have different manifestations or properties in these realities. For example, if certain forms of dark matter interact with the fabric of space-time in unique ways, they could create pathways or distortions that connect our universe to others. This interaction can lead to gravitational effects that leave visible traces within our universe, even if other universes remain inaccessible. In addition, the dynamics of dark matter may provide insight into how universes may evolve. Because dark matter influences the formation of galaxies and large-scale structures, understanding its behavior could reveal how similar structures might arise in other universes under other physical laws. For example, if the composition or properties of dark matter change, this could lead to divergent evolutionary paths of cosmic structures, not only in our universe, but also in neighboring universes. The nature of dark matter also suggests that studying it could provide insights into fundamental physics, potentially bridging gaps between our understanding of quantum mechanics and the general theory of relativity. If dark matter is found to be associated with quantum effects, this could point to a more intricate network of interactions that may extend beyond our universe. The potential existence of hidden dimensions or alternate realms, as hypothesized in some models of dark matter particle physics, could open the way to theories about the connections between universes. Studying the implications of dark matter not only helps unravel the mysteries of our universe, but also inspires the search for the larger structure of reality itself. As scientists continue to investigate the properties and role of dark matter, we are constantly challenged to think about the limits of existence and the potential for interactions with other universes, ultimately expanding our understanding of the overarching cosmic landscape in which we live. The study of quantum gravity aims to unify the principles of quantum mechanics and the general theory of relativity, solving one of the most significant problems in modern theoretical physics. By understanding how gravity behaves at the quantum level, researchers hope to penetrate the fundamental fabric of reality, particularly what may exist beyond our universe. One of the most important aspects of quantum gravity is its potential to reveal the nature of space-time itself. Many theoretical approaches, such as string theory and loop quantum gravity, suggest that space-time is not a continuous entity, but rather is constructed from discrete elements or fundamental strings. Such a perspective allows for the possibility that our universe is part of a larger and more complex structure, where the geometry of space-time may have other properties in regions beyond the boundaries we observe. Such a framework can lead to a better understanding of how other dimensions or universes may interact with our own, offering a glimpse into potential complexities that lie beyond the familiar fabric of our reality. In addition, quantum gravity could provide insight into scenarios involving black holes and singularities. When matter collapses into black holes, the ordinary laws of physics break down, leading to conditions that challenge our understanding of time and space. The study of these extreme environments may reveal information about the information structure of black holes, which may serve as conductors or portals linking to other regions of the universe or even alternate universes. This could pave the way for theories that posit that information is never lost and suggest that connections between universes may exist through gravitational interactions and transitions. Moreover, progress in understanding quantum gravity could lead to new paradigms in cosmology, especially in explaining cosmic phenomena such as inflation or the Big Bang itself. If a deeper theory of quantum gravity can accurately describe the dynamical processes of the early universe, it could indicate how regions of space-time emerged, potentially hinting at the existence of other universes created within an overarching multiverse. This can change our understanding of the expansion and evolution of the universe, revealing the influence of dimensions or realities beyond our perception. In this way, the study of quantum gravity can greatly expand our understanding of fundamental aspects of the cosmos, bridging gaps between observed phenomena and theoretical frameworks. As researchers explore the implications of quantum gravity, they may increasingly uncover knowledge that will not only enlighten us about the universe we live in, but also expand our understanding of what exists beyond its observable boundaries, pushing the limits of human knowledge into uncharted territory. The concept of a multiverse landscape arose primarily from string theory and cosmological considerations, suggesting that our universe is just one of many, each with its own unique physical laws and constants. This landscape is often visualized as a vast collection of possible vacuum states, where different regions of the landscape correspond to different configurations of fundamental parameters. Each configuration can give rise to a unique universe with different properties, from variations in the forces of nature to differences in dimensional structures. Researchers have used a variety of theoretical and computational approaches to study the landscape of the multiverse. One important method involves analyzing the mathematical formulations of string theory, which inherently predict a vast number of solutions corresponding to different states of the vacuum. By studying these solutions, physicists can identify potential physical characteristics and their consequences, allowing them to investigate how specific conditions can lead to observable outcomes in different universes. In addition, researchers use cosmological and astrophysical observations to support the multiverse hypothesis. For example, anomalies observed in the cosmic microwave background radiation, or the large-scale structure of our universe, may provide indirect evidence for the interaction or influence of other universes. Scientists analyze current observational data to test the predictions made by various models of the multiverse, and look for patterns that might suggest the underpinnings of the broader landscape of the multiverse. In addition, numerical modeling plays an important role in studying the landscape of the multiverse. By creating computational models that simulate cosmic evolution under different sets of parameters, researchers can study how different configurations can manifest themselves in the formation of structures, the distribution of galaxies, and even the fundamental behavior of particles. These simulations provide valuable insights, allowing scientists to compare predicted results with observations of our universe. Finally, discussions about the implications of fine-tuning and the anthropic principle are important in the context of the multiverse landscape. The anthropic principle suggests that the observed values of physical constants in our universe are not random, but are compatible with the existence of observers like us. This perspective can help researchers characterize the landscape of the multiverse. It also opens the door to discussions about why some universes have some conditions favorable to life, while others remain inhospitable. Overall, the concept of the multiverse provides fertile ground for investigations into the fundamental nature of reality, pushing the boundaries of theoretical physics and guiding the search for complexities that lie beyond our universe. As scientific methods and technology advance, the study of the multiverse landscape may reveal deeper connections between the diverse realities that populate this theoretical structure, enriching our understanding of the cosmos and our place in it. Future space telescopes and observatories have great potential to expand our understanding of the boundaries of the universe in several important ways. By placing advanced instruments outside of Earth's atmosphere, scientists can overcome many of the limitations imposed by atmospheric distortion and light pollution, allowing for clearer and more detailed observations of distant cosmic phenomena. These telescopes can operate over a wider range of wavelengths, expanding our ability to study the complex structure of the universe and beyond. One of the key areas where space observatories can improve our understanding is in the study of distant galaxies and the large-scale structure of the universe. Observatories equipped to take images in the infrared, ultraviolet, and even sub-millimeter wavelengths will allow astronomers to detect the light of the earliest stars and galaxies formed after the Big Bang. By studying these distant celestial bodies, scientists will be able to trace the evolution of the universe, better understand the history of its expansion, and explore the formation of cosmic structures that lie at the edge of the universe we observe. In addition, modern telescopes will allow for a better understanding of dark matter and dark energy, two enigmatic components that influence cosmic dynamics. Instruments designed to map gravitational effects from dark matter and measure the expansion rate of the universe can provide crucial insights into these phenomena. By characterizing these elements, scientists will be able to refine our models of cosmic growth and ultimately expand our understanding of structures and influences beyond the observable boundaries. In addition, future space observatories will enhance our ability to detect gravitational waves, especially through missions designed for gravitational wave astronomy. Observatories, such as those based on the concept of a space antenna with a laser interferometer, will be able to measure the gravity of the universe. Telescopes will be able to measure gravitational waves from merging black holes and neutron stars on cosmic scales. These capabilities will allow us to understand high-energy events occurring far beyond our galaxy and potentially link us to phenomena that shape regions of space far beyond our observable universe. Finally, space telescopes can not only observe the known universe, but also contribute to a more detailed study of the cosmic microwave background radiation. Improved accuracy in mapping temperature fluctuations can provide information about the conditions of the early universe and potentially reveal aspects of cosmic inflation or anomalies that hint at structures that lie beyond observable boundaries. As these technologies and missions develop, they will allow researchers not only to look deep into space, but also to answer fundamental questions of existence about the boundaries of the universe and its larger structure. The resulting data could overturn our view of the universe and lead to new theories about the nature of reality, as well as shed light on the complex connections that may exist between our universe and others beyond our current observational range. Artificial intelligence has the potential to play a transformative role in developing and testing theories about what lies beyond our universe, particularly through improved data analysis, simulation, and theoretical modeling. As the amount of astronomical data continues to grow exponentially, artificial intelligence techniques can help researchers efficiently process vast amounts of data, identify patterns, and draw conclusions that may not be readily apparent using conventional methods. One of the main applications of artificial intelligence is analyzing data from telescopes and observatories. Machine learning algorithms can be trained to detect subtle signals or anomalies in noise, helping astronomers distinguish genuine astrophysical events from false data. For example, AI can analyze the cosmic microwave background radiation to identify irregularities or anomalies that may indicate the influence of spheres beyond our observable universe, and guide further research into the multiverse or other cosmic phenomena. AI can also improve the modeling of complex physical systems and the simulations used to explore theoretical predictions. In the fields of cosmology and particle physics, researchers often rely on computational models to simulate the behavior of matter and energy under different conditions. Artificial intelligence techniques can optimize these simulations, allowing scientists to explore a wider range of scenarios and factors, potentially revealing new aspects of how different types of matter and dark energy interact. This predictive ability could help test existing theories and create new hypotheses about what may exist beyond the observable cosmos. In addition, artificial intelligence can help refine theoretical frameworks by quickly assessing the viability of competing models. For example, AI can evaluate how well different theories explain observed phenomena, or create predictions that can later be compared to real-world data. This allows them to optimize the scientific process and focus on the most promising theories concerning the structure of the universe or its connections to alternate realities. In addition, AI's natural language processing capabilities can facilitate researcher collaboration by synthesizing vast amounts of scientific literature. By identifying relevant research, identifying relationships between findings, and generalizing research, AI can foster the interdisciplinary dialogue that is needed to address complex questions about what lies beyond our universe. Overall, the integration of artificial intelligence into astrophysics and cosmology promises to greatly expand our understanding of the universe and its underlying structures. As AI tools develop and improve, they are likely to become valuable resources for deep space exploration, leading to breakthroughs in our perception of reality and the possible connections we can discover beyond our observable universe. Advances in particle physics, especially at facilities such as the Large Hadron Collider, have the potential to greatly expand our understanding of multiple universes, allowing us to answer fundamental questions about the nature of matter, energy, and the forces that govern the cosmos. By conducting high-energy collisions at the Large Hadron Collider, scientists are investigating the behavior of subatomic particles under conditions that mimic those that existed shortly after the Big Bang. This experimental approach not only allows us to understand the fundamental constituents of our universe, but also to explore theories that suggest the existence of multiple universes. One potential contribution of the Large Hadron Collider to the concept of the multiverse is to search for new particles and interactions predicted by extensions to the standard model of particle physics. For example, some theories, such as supersymmetry or string theory, suggest the existence of a richer set of particles than those currently known. The discovery of these new particles could provide evidence for the existence of multiple dimensions and energy states associated with multiverse theories. If researchers discover phenomena such as extra dimensions or previously unknown particles, It could support the idea that our universe is connected to others in a more complex, multidimensional structure. In addition, the study of the properties of the Higgs boson plays an important role in understanding the conditions for the existence of the early universe. The discovery of the Higgs boson at the Large Hadron Collider confirmed one of the major predictions of the Standard Model, but its implications are still being explored. The mechanism underlying the Higgs field and how it interacts with other particles could shed light on the mechanism of cosmic inflation, the early rapid expansion that is thought to have laid the groundwork for the structure of our universe. If inflation can be linked to a broader theory involving multiple universes, deepening our understanding of the Higgs boson could then also open up opportunities to explore these connections. In addition, high-energy collisions in particle-gas petals, such as the Large Hadron Collider, can provide insights into the dynamical processes of the early universe, including phase transitions that could lead to other universes. Theoretical models suggest that in a multiverse scenario, different vacuum states could be observed in different regions, leading to separate universes with their own physical laws. By studying the behavior of particles under extreme conditions, it could provide clues to the processes that lead to these cosmic bifurcations. Finally, advances in particle physics from experiments at the Large Hadron promising theories concerning the structure of the universe or its connections to alternate realities. In addition, AI's natural language processing capabilities can facilitate researcher collaboration by synthesizing vast amounts of scientific literature. By identifying relevant research, identifying relationships between findings, and generalizing research, AI can foster the interdisciplinary dialogue that is needed to address complex questions about what lies beyond our universe. Overall, the integration of artificial intelligence into astrophysics and cosmology promises to greatly expand our understanding of the universe and its underlying structures. As AI tools develop and improve, they are likely to become valuable resources for deep space exploration, leading to breakthroughs in our perception of reality and the possible connections we can discover beyond our observable universe. Advances in particle physics, especially at facilities such as the Large Hadron Collider, have the potential to greatly expand our understanding of multiple universes, allowing us to answer fundamental questions about the nature of matter, energy, and the forces that govern the cosmos. By conducting high-energy collisions at the Large Hadron Collider, scientists are investigating the behavior of subatomic particles under conditions that mimic those that existed shortly after the Big Bang. This experimental approach not only allows us to understand the fundamental constituents of our universe, but also to explore theories that suggest the existence of multiple universes. One potential contribution of the Large Hadron Collider to the concept of the multiverse is to search for new particles and interactions predicted by extensions to the Standard Model of particle physics. For example, some theories, such as supersymmetry or string theory, suggest the existence of a richer set of particles than those currently known. The discovery of these new particles could provide evidence for the existence of multiple dimensions and energy states associated with multiverse theories. If researchers discover phenomena such as extra dimensions or previously unknown particles, it could support the idea that our universe is connected to others in a more complex, multidimensional structure. In addition, the study of the properties of the Higgs boson plays an important role in understanding the conditions for the existence of the early universe. The discovery of the Higgs boson at the Large Hadron Collider confirmed one of the major predictions of the Standard Model, but its implications are still being explored. The mechanism underlying the Higgs field and how it interacts with other particles could shed light on the mechanism of cosmic inflation, the early rapid expansion that is thought to have laid the groundwork for the structure of our universe. If inflation can be linked to a broader theory involving multiple universes, deepening our understanding of the Higgs boson could then also open up opportunities to explore these connections. In addition, high-energy collisions in particle-gas petals, such as the Large Hadron Collider, can provide insights into the dynamical processes of the early universe, including phase transitions that could lead to other universes. Theoretical models suggest that in a multiverse scenario, different vacuum states could be observed in different regions, leading to separate universes with their own physical laws. By studying the behavior of particles under extreme conditions, it could provide clues to the processes that lead to these cosmic bifurcations. Finally, advances in particle physics from experiments at the Large Hadron Collider could also expand our understanding of dark matter and dark energy, the mysterious components that determine the mass-energy budget of the universe.